So today we will talk about two-path interferometers, and I have began drawing one here. So a quantum object comes in a particle. That could be a photon or a neutron or an atom. And then we have a preparation stage here that prepares the atom for going through the interferometer. And then finally we probe. And so through the interferometer, we can take the path along the bottom left corner. So we go around here and go to this detector, and this is what we call path 1. And then that goes to the detector that I will indicate by D1. And then there is the detector D2. And we reach the detector D2 by following path 2, which goes around the top right corner. Now, if we use a mirror at the bottom right corner, then every particle that follows path 1 goes to detector 1. Every particle that follows path 2 goes to detector 2. And so if we do that, then we operate the interferometer in particle mode. Now, let's imagine that we have this particle mode, so the mirror is there, and we send one particle through, and another particle through, and a third particle through, and we record whether detector 1 or detector 2 registers the particle. After we have done this very, very many times, we have found fraction W1 detected at D1 and fraction W2 detected at D2, and of course these two fractions add up to the full fraction, which is 100% 1. Now, in some sense, having having knowledge of these fractions, we know something about how likely it is for the next particle to take path 1 and path 2. So once we have found these fractions W1 and W2, we can actually use this information to make a guess about where the next particle will land. So we send a particle in, and then we try to guess whether detector D1 will register that particle or detector D2. If we just make a random guess, then that will be correct with a probability of 1/2, because we will sometimes guess right and we will sometimes guess wrong, and if we make use of no other available information, well, that's what we should expect. Now, if we make use of this information and thereby guess in a more clever way, we will have a larger likelihood for guessing right. So the likelihood for guessing right will be this 1/2 plus another term, which is 1/2 of the number that represents our knowledge of the path. And of course, the total likelihood cannot exceed 100%. So this is bounded from above by 1, and therefore the knowledge is a number that cannot exceed 1. And of course, it will be positive because it describes the excess over the 1/2 of the purely random guess. So what is the best strategy that we can use for guessing? Well, the best strategy that we can use is that we always bet on the path which has the larger probability W1 or W2. So we will bet on path 1 if W1 is larger than W2, and we will bet on path 2 if W2 is larger than W1, which means that our likelihood for guessing right is the larger of the two numbers W1 and W2, And the maximum of two such numbers is simply the sum plus half the difference, absolute value of the difference. Now the sum is 1, so we get half plus half the difference of W1 and W2. And so the largest value for k that we can get by this best guessing strategy is this difference between W1 and W2. And so the knowledge that we get here would be W1 minus W2 absolute value. And this kind of knowledge we call the path predictability and denoted by the letter P. So the predictability is the maximum knowledge that we can demonstrate by guessing right as often as we can. We've talked about operating the interferometer in particle mode, where we probe with a mirror. We have path probabilities W1 and W2 for path 1 and path 2, and the absolute value of their difference is the path predictability. So if one probability is very large and the other one is very small, the path predictability is high. We have a good chance of guessing the path right. If the probabilities are both close to 50%, then the predictability is low. Now, we can also operate the interferometer in what we will call wave mode. And for having wave mode, we use a half-transparent mirror at the bottom right corner. So this half-transparent mirror makes sure that if I block one path, say I block this path, then I know all particles come path 2, and a half-transparent mirror will distribute them equally to detector 1 and detector 2. So half of the particles that arrive along path 2 will go to detector 1, half of the particles will go to detector 2. Similarly, if I block path 2, then all particles are known to arrive along path 1, and again, because of the half-transparent mirror, half of those particles will end up in detector 1, half will end up in detector 2. So this tells me that I'm working in wave mode. I check that if I block one path, both detectors click with equal frequency. And that should be true for path 1 and for path 2. Now, a half-transparent mirror is not the most general thing that gives me this situation, because I have also the option of introducing a relative phase between the two paths, and that relative phase I will denote by phi. So now we operate the interferometer in wave mode. We manipulate the phase, and we can do that by either changing the path length a little bit by moving the mirrors that are not drawn at these corners at the bottom left and top right, and thereby moving the mirrors, thereby making the path a little bit longer, a little bit shorter along one arm of the interferometer. Or, say, if I'm using photons, I can use a refractive material of a variable length and thereby introduce a phase between the two paths. Or there are other methods. Anyway, we have a way of setting the phase and controlling it. So now we choose a value of the phase, we send a lot of particles through, and we count how often is the particle registered by detector 1, how often by detector 2. Then we change the phase, we send more particles through, we check how often we get the particle registered by detector 1, detector 2. We do that for a third phase, we do that for a fourth value of phi, and so forth. After we have done this for very many values of phi, we plot as a function of phi the relative frequencies of detecting the particle at detector 1 and detector 2. So this will be numbers between 0 and 1. A half is here, and then for a particular phi, we will have some values which are larger than a half, and for other phi's we will have values which are less than a half. So we could have a pattern that looks like this for detector 1, and a pattern that looks like this for detector 2. And then we just look at what is the largest value that we have and what is the smallest value that we have. And we take this largest value that we have, we subtract the smallest value, we divide by the sum, and then this is what is called the fringe visibility for such an interference pattern. So we operate the interferometer in this wave mode, and we see an interference pattern. For that we need a relative phase between the paths that we can adjust, and that's what we get by operating the interferometer in this way. So if we operate the interferometer in particle mode, we have these path probabilities, which we talked about how to find them, and then there's a path predictability, which we find from as the difference of these probabilities, and then we have the option of using the wave mode, and then we see interference fringes, and they have a visibility for which we have this expression. Now, the so-called wave-particle duality in this extreme situation would tell us that if we have quantum objects that we can regard as particles, because for each of one we know where it is all the time, so we have full knowledge about the path, then we should not have any wave aspects present, so we should not have any fringe visibility. And this is sort of what we discussed already. If one path is blocked, or for some other reason we know for sure that the particle follows one path, then the two probabilities for detecting the particle at D1 or D2 are equal, and that will be independent of the value of phi, and we have no fringes that have and there's no fringe visibility. The other extreme, with full fringe visibility, so precludes any path knowledge, and so if the visibility is very high, the predictability has to be very small, or if the visibility is maximal, we have fringes with full visibility, there should not be any path predictability. So those are the extreme cases of having full particle description or full wave description. But what are the compromises allowed by the quantum nature of these particles? So now let's see how we go about describing the situation using the quantum formalism. So this binary alternative of following one path or another, that's just a path qubit. And for the statistical operator of a qubit, we can always write a 2x2 matrix. So the 2x2 matrix in this case will have W1 and W2 on the diagonals, because those are the probabilities for the paths that we can determine by having a mirror here and counting particles at D1 and D2. And then there are off-diagonal matrix elements, and they will be of the form a number epsilon and the square root of W1 and W2, epsilon complex conjugate square root of W1, W2, where epsilon is a complex number that is between 0 and 1, because otherwise this row would not have the correct properties. And those correct properties are that the row is equal to its adjoint. Well, that's why we have epsilon complex conjugate here and epsilon there. And the trace of row has to be 1. Well, that trace is the sum of the diagonal matrix elements. So that's just, again, the statement that W1 plus W2 has to be equal to 1. So that's built into it. And then also that the determinant of rho, that will be a number between 0 and a quarter. And let's see what that tells us. What is the determinant? The determinant of rho is equal to W1, W2 minus the absolute value of epsilon squared times W1, W2. And yes, this is W1, W2, 1 minus the absolute value of epsilon squared. And so, since W1 and W2 add up to 1, the product of these positive numbers cannot be more than a quarter. And since the epsilon is between 0 and 1, this whole expression will not be more than a quarter. So that's correct. So we have this matrix for the particle as it is prepared at the preparation stage, with this restriction on the determinant. Now, particle goes through the interferometer and the phase is shifted. So the phase shifting we will describe by a unitary matrix which imposes phase e to the I phi half on path 1 and e to the minus I phi half on path 2. So with this phase shifting, the rho is turned into rho after the phase shift, rho phi, which is equal to this e to the I phi half 0, 0, e to the minus I phi half acting on rho from the left, and its adjoint e to the minus I phi half 0, 0, e to the I phi half acting on the right. So we get no effect on the diagonal matrix elements, because for the diagonal matrix elements I'm getting these two phase factors that compensate for each other, or these two phase factors that compensate for each other. So it's W1 and W2 on the diagonal matrix elements. But this off-diagonal matrix element will get a phase e to the I phi half from here and another phase of e to the I phi half from here. So this will be multiplied by e to the I phi, and then we have the epsilon complex conjugate and the W1, W2. And for this off-diagonal matrix element, we get two factors of e to the minus I phi half. So the overall effect will be introducing a phase of e to the minus I phi, and other than that, the matrix element is as before. We have now arrived here in the interferometer, and this is the matrix describing the state of the path qubit. Now, if we are in particle mode and there's the mirror here, then the mirror does not do anything to the path. So the mirror would just be described by the 2 by 2 identity matrix. And so if we incorporate the effect of the mirror, then we would multiply this rho phi from the left and from the right by the same identity matrix, and it would just be still the rho phi. And now we are looking for the probability for detector 1 and the probability for detector 2. And so we pick out those matrix elements. So for detector 1, it is the 1, 0 rho, and then it's the rho phi, because the mirror doesn't do anything. So this is still the same 2 by 2 matrix for the state of the qubit, and that just 1, 1 just picks out the top left element in the matrix, and that's W1. Well, that's what we should have expected, and in a sense that's what we put in by writing this matrix. And same for the probability of detecting the particle at D2. Here we have the 0, 1 row and the 0, 1 column, and we pick out W2. So that's exactly what we expect, and it confirms that the phase that we introduce has no consequence when we operate the interferometer in particle mode. Now let's look at wave mode. For wave mode we have the half-transparent mirror, and that half-transparent mirror, for that we need to write a unitary matrix that takes what comes from path 1 and distributes it evenly on the D1 output port and the D2 output, and the same for path 2. And so I will use the following matrix for this purpose: 1 I1 divide by the square root of 2 to make it unitary. So if we now look for the probability for D1, what we will have to calculate is the 1, 0 row. Then we have this unitary matrix for the half-transparent mirror. Then we have the row phi, which is the phi before we get to the half-transparent mirror. And then we have the adjoint of the matrix for the half-transparent mirror. And finally, we have the 1, 0 column for looking at the probability for detector 1. And so this is half. And then if we just look here, this will give us 1 minus I. And here we have row phi. And on the left, we get 1 minus I adjoint. And so we work this out, and what we find is a half plus the imaginary part of e to the minus I phi epsilon times W1, W2. So that's the probability for detector 1, and the probability for detector 2. We can work this out in the same way, and then we find half minus the imaginary part of e to the minus I phi epsilon times the square root of W1, W2. So this phi dependence here and here, well, that's the interference pattern that we talked about earlier when we established the notion of the fringe visibility. And so what we will need to find the fringe visibility is the maximum and the minimum of these probabilities. And in both cases, the maximum is half plus the absolute value of epsilon square root W1, W2. That happens when we choose the phase such that the product of e to the minus I phi times epsilon is just equal, it's I times the absolute value of epsilon. Then this just becomes the absolute value. And for the minimum, we have a minus sign here. So what do we find? We find that the fringe visibility is equal to maximum minus minimum. So that's 2 absolute value of epsilon square root W1, W2 divided by the sum, which is 1. So what we have now found is that quantum particles sent through this interferometer, and every one of them prepared such that this matrix describes the path qubit after the preparation. In that situation, we have a path predictability, which is the absolute value of the difference of the diagonal matrix elements, and we have a fringe visibility, which is 2 times the absolute value of epsilon and the square root of W1 and W2. So the path knowledge has to do with the diagonal matrix elements, and the visibility is directly related to the off-diagonal matrix elements. Now, let's just check. What if the path knowledge is equal to 1? then that requires one of the w's to be equal to 1 and the other one to be equal to 0, in which case this product is always 0 and the visibility has to be 0. So if the path notice is 1, then the visibility is surely equal to 0. What about the situation that the visibility is 1? We have fringes with full fringe visibility. Okay, so how do we get 1 here? Well, we get 1 here if the epsilon is 1, then this product is 2, and then each of the w's has to be equal to a half, because otherwise the square root will always be less than a half. So we get 2 times 1 times a half, and that gives the visibility 1. But as I just said, the two w's have to be equal to a half, and they're both of them equal to a half, and then the difference is 0. So we have no path predictability when the visibility is 1. What about compromises? Okay, let's see what we can say about that. So I will look at P first and take a look at the square of P. So that's the W1 minus W2 squared. And that is in turn equal to W1 plus W2 squared minus 4 times W1 W2. So this is equal to 1 minus 4 times W1 W2, because the W1 plus W2, the trace of rho is 1. So now I'm taking this P squared and I'm adding V squared to it. So the P squared is 1 minus 4 W1 W2, and the V squared is 4 W1 W2 times epsilon squared. So I have the V squared added by having minus minus epsilon squared, so it's plus 4 W1 W2 epsilon squared. And now we look here and we recognize that this is 1 minus 4 times the determinant of rho. Right, so the determinant at most can be equal to a quarter when all of this is 0, but we already know that this sum of P squared plus V squared cannot be less than 0. And the smallest value for the determinant of rho that we can have would be 0. That happens when the epsilon squared is equal to 1. Then the determinant of rho is 0, and that gives us the largest value that we can reach for P squared plus V squared, and that's 1. So in summary, the compromises allowed by quantum physics is P squared plus V squared less than 1. And this is a quantitative statement about wave-particle duality. Now let me remind you that this result of this quantum mechanical description of the experiment is not something that is already contained in the way the path predictability and the fringe visibility are defined, because we define them in an operational way. The path predictability is a number we established by operating the interferometer in particle mode, with no reference to the quantum mechanical formalism. The fringe visibility we determine by operating the interferometer in wave mode, again, with no reference to the quantum mechanical formalism. So the values of P and V are established by a certain operational procedure, by a certain way of doing experiments. Now quantum mechanics tells us that P squared plus V squared must not exceed 1. And now this is a prediction, quantum mechanics, about these operationally defined quantities, path predictability and fringe visibility, which we can test by conducting such experiment and by verifying whether in real experiments we really have the situation that always the P squared plus V squared is less than 1. And indeed, if we do such experiments, there are no cases where P squared plus V squared exceeds 1. So this quantum mechanical prediction, this quantum mechanical statement about the compromises allowed between particle aspects and wave aspects is really a correct statement about the nature of these quantum particles. Alright, so we have established this inequality, and clearly it contains the cases that we have talked before. So we have P equals 0 when V is equal to 1, because if the V is equal to 1, then this square is already 1, there's nothing left for the P. And we have V equals 0 when P is equal to 1, which are these extreme cases where we have only particle properties and only wave properties, or only particle aspects, only wave aspects present in the experiment. But what about compromises? Imagine that we are running the interferometer such that we have a likelihood of guessing right, which is 99%, which means that almost always we will guess the path right. Now the likelihood, remember, is half plus half times the predictability for the optimal strategy of guessing, and so the predictability is 0.98 in this case. So how much visibility is possible? So the visibility is then now bounded from above by 1 minus this p squared, and that is about 0.2 if you put in these numbers. So which is to say that in a situation where we can guess the path right, almost always we get it wrong only for 1 in 100 particles or 10 in 1,000 particles. We can still have interference fringes with a visibility of 20%. And those are fringes which are very easily recognized by the naked eye. So those are fringes with a good visibility. So there's a lot of room between these extreme cases where we know nothing about the path and we have full fringe visibility, or we have perfect path knowledge and no visibility. We can have a lot of path knowledge, P equals 0.98. We guess right in 99 out of 100 cases, and still we have fringes with a very good visibility. So now let's add a twist to what we have done. We have seen that if we operate the interferometer, we will have particle properties quantified by the predictability, wave properties quantified by the visibility, and the p squared plus v squared is less than 1. But now imagine that the preparation that we do here allows us to identify different subensembles, put labels on the particles such that particles with label k together have a predictability pk and a visibility vk, and of course the pk squared plus the vk squared cannot exceed 1. And then we have particles with a different label and a different value for the predictability, a different value for the visibility, but again the sum of the squares cannot exceed 1. And this kth kind of particle occurs with a probability that we call pk. Now, if you think about the guessing game that we had originally to identify the path knowledge, well then, if you know that particle carries the label k, you will guess according to the probabilities assigned to the paths there. So you will bet on the most likely path for particles of the type k. And if you have another value of k, well, then you will again check which path is more likely for those particles, and you will always bet on the path which is more likely. So your overall likelihood of guessing right will just have an overall path knowledge which comes about as a weighted sum of the predictabilities for the individual kinds of particles and the probability with which they occur. So put differently, we are sorting the whole big ensemble of particles into subensembles labeled by k. For each subensemble we have a predictability and a visibility, and the sum of the squares is less than 1. And the subensembles have different size, for which we have this probability pk. So for the next particle to come, it has this probability pk of ending up in the kth subensemble, and then taking everything together, optimizing our betting strategy now that we have additional knowledge, because we know that the particle we are talking about belongs to the kth subensemble, then we bet according to that, and this gives us an overall path knowledge k. Now for the visibility, we will also now have different values of the visibility in the different ensembles. So there could be some ensembles for which the visibility is high, but the predictability is low. Other subensembles for which the predictability is high and the visibility is low. So say we have managed to sort in subensembles where every one has a high visibility, then the overall visibility is high. Okay? So we also have an average visibility that we get by the weighted sum of the individual visibilities. So I will call this average visibility to distinguish it from the visibility of the ensemble as a whole. Now, the knowledge that we gain here by this sorting, that will not be less than the knowledge that we have without the sorting. So this k is necessarily larger than the predictability for the ensemble as a whole. And likewise, this visibility cannot be less than the visibility of the unsorted ensemble. But what about the knowledge squared plus the average visibility squared that we get from the sorting? So that is equal to the sum, and now let me write KL, PK, PL, predictability K, predictability L. So this double sum is the square of K. And then we have a similar double sum for the square of the average visibility. So we have another term, which is VK VL. Now, but this sum of these products PK PL, this sum is always less than what we get if we look at the individual sums of squares and take square roots. So there's the PL squared and the VL squared and the square root. And so this product, the sum of products is never more than this product of square roots of sums of squares. Now every one of them is less than 1. So also this product of the two square roots is less than 1. So we have now found that the k squared plus the v average squared is less than the sum over k pk times the sum over LPL. But of course, these probabilities add up to 1. And so we have 1 times 1, which is equal to 1. So the bottom line is that even with this sorting, we have the same inequality, but now for the average quantities that we get for path knowledge and fringe visibility for the sorted subensembles. So this is the average predictability for all the subensembles, weighted by how many particles, which fraction of the particle is in the respective ensemble, and the same for the visibility. Now this opens the door for additional possibilities where we can set up the experiment such that we can sort into subensembles that have large predictability. Then this K will be as large as it can possibly be, but remember that the average visibility is bounded from below by V. So the K that we can have is bounded from above by 1 minus the V squared, where this V is the V of the full ensemble. And the average visibility that we can have, if we do the sorting such that we gain a lot of visibility that isn't there originally, then this is still bounded by 1 minus the predictability squared of the original ensemble.